Assalamualaikum, idem Nuriza Muhammad Yusof. So my name is Muhammad Nazir bin Muhammad Nizam. So as for introduction, from subtopic chapter 2, our group has been chose fundamental theorem of line integral. So in this chapter, the theorem is used for calculating the total work done for some vector field. And this theorem states that the total work done is depend on the force taken for a moving object over distance instead of considering the path taken. So as a simple example, we consider two cars moving forward to places with the same starting line and finishing line, but with a different path. So both of the car will face the different traffic and challenge around the road. So the theorem is considering the traffic and challenge instead of the distance to reach to a places. So these theorems can be applied for a specific condition. Firstly, the curve C must be piecewise smooth from the start and end point. And secondly, line integral of vector field F along curve C must be independent paths. And lastly, the vector field F must be conservative fields. So as for two-dimensional space, we need to check the partial derivative for a function with respect to x and y is equal. Then for three-dimensional space, we must show that the curl F is equal to 0. So this application will be explained detail later on with the question given. For a further explanation on the theorem, we can take a look of this graph. So we can see that two different curves and one straight line with the same start point and end point. It shows that C1 and C2 and C3 with a different function has a different path connecting to the same point. So in conclusion, it demonstrates the independent paths of the conservative vector fields. So it applies to the condition of the fundamental theorem line of integral. So for question 1, it stated that a particle move in two-dimensional force field defined by the vector field fxy is equal to 2xy plus 3i plus x squared minus 1j. So the particle moved from point A 1 2 to the point B 3 4. So for question A, on the Cartesian plane, sketch the point A and B. Draw two different possibility paths, one straight line and one curve, connecting these points, and label these paths as C1 and C2. So as for question 1A, so on a Cartesian plane, it states that to sketch the point A and B for two possible paths. So as you can see at graph 1, we sketch on Cartesian plane for a straight line from point A12 to B34 as a C1. And for graph 2, we sketch for a curve from point A12 to B34 and stated as a C2. We can see the curve is like that. And so as can you see from graph 3, the combination of straight line and curved line. So as we can see, from the combining line and the curve, it shows the independent paths taken from the function. Thus, we can see the two paths is piecewise smooth without any intersection from others. As for question 1b, using the fundamental theorem of line integral, calculate the total work done by the field as the drone moved from C1 to C2. So, to find the total work done by this theorem, step 1, we must show that F is conservative vector field. So we let Pxy and Qxy to find the partial derivative. So we let the function P is equal to 2xy plus 3, and we let function Q is x squared minus 1. So we differentiate P in respect to y, and we differentiate Q with respect to x. So we gain the same exact value, which is 2x. So it shows that the F is conservative. So for step 2, we must find the potential function. So we integrate both of the function, which is when we integrate function P, we get x squared y plus 3x, and we integrate for Q, for dy, we get x squared y minus y. So the potential function is x squared y plus 3x minus y. So we have applied the condition of the fundamental theorem of line integral. So we can find the total work done by applying the theorem. So from the potential function that we gain, which is x squared y plus 3x minus y, we substitute the initial points A and endpoints B to the function. So as you can see from the calculation that we gain 38 for total work done by the field as the drone moved from C1 to C2. So that's all for the question 1.
So to start, let's look at the scenario for question 2. So we are monitoring a surveillance drone mission that takes place in a specific 3D region. The region where the drone flies isn't an empty space. It has a wind force. This force is defined by a potential function which is fxyz equal to xy plus z squared. So the mission has two specific visa points. It begins at the origin, which we label as point P, which is coordinate as 0, 0, 0, and it ends at the designated landing pad labeled as Q, which is coordinate at 2, 2, 1. So now because there are obstacles in the way, the drone cannot fly in a straight line. Instead, it must follow a curved 3D parabolic trajectory to reach its destination safely. So based on this setup, the problem asks us to perform two tasks. First, we need to provide a sketch of path C. So this is a visual representation of that smooth curved flight from the start point at the origin to the landing pad. And second, we need to calculate the total work done by the wind force field during this flight. To make this calculation possible, the problem instructs us to use the fundamental theorem of line integral, which is FTLI. So the key question we are answering here is how much effort or work did the wind field exert on the drone as it moved from point P to Q along that specific curve path. Next, I will show you how to sketch the drone's flight path, which we call path C. We can break this down into four simple steps. Step 1, draw the 3D axis. First, we set up our 3D coordinate system. Draw your x, y, and z axis. Label the origin as point P, which is coordinate at 0, 0, 0. And this is our starting point where the drone takes off. Step 2, plot the destination point Q. Now let's locate the landing pad. From the origin, move 2 units along the x-axis, 2 units along the y-axis, and 1 unit out the z-axis. Mark this as point Q, 2, 2, 1. Step 3. Sketch the trajectory. Since the drone follows a parabolic trajectory, we don't draw a straight line. Instead, we draw a smooth gentle arc connecting P to Q. Step 4. Label the path. Finally, add an arrow pointing from P toward Q to show the direction of travel and label this as curve as path C. So now let's move on to the calculation. We need to find the total work done by the wind force field as the drone moves from point P to point Q. To do this, we use the fundamental theorem of line integrals. The core concept, the theorem states that if you have a potential function, the work done is simply the difference in the potential between the final point and the starting point. In other words, the specific path the drone took doesn't change the final result. Step 1. The function. Our given potential function is fxyz equal to xy plus z squared. Step 2. Evaluate at the start point P. First, we plug in the coordinates for our starting point P equal to 0, 0, 0. As you can see, f0, 0, 0 equal to 0 multiplied to 0 plus 0 squared, which equals to 0. Step 3. Evaluate at the end, which is point Q. Next, we do the same for our landing pad Q, which coordinates at 2 to 1. Plugging these values into the function gives us f2 to 1 equal to 2 multiplied to 2 plus 1 squared. This equals to 4 plus 1 equals to 5. Um, Step 4, find the difference. Finally, we subtract the starting value from the final value, which is 5 minus 0 equal to 5. So therefore, the total work done by the field as the drum moves from P to Q is exactly 5 units. So now let's move on to the calculation. We need to find the total work done by the wind force field as the drone moves from point P to point Q. To do this, we use the fundamental theorem of line integrals. The core concept, the theorem states that if you have a potential function, the work done is simply the difference in the potential between the final point.
In our first question, we analyzed a two-dimensional conversative field. The primary objective was to demonstrate the principle of path independence. The graph displays two distinct routes from point A12 to B34. C1 represents a direct linear path while C2 follows a parabolic curve. To prove the field is conservative, we use the sp.different function to calculate partial derivative and compare them to ensure delta m over delta y equal to delta n over delta x. We define the potential function fsy in the script and use the substitution function to evaluate the potential at the endpoint. The output confirmed that the work done is 38 units, proving that regardless of whether the particle follow the straight or curved path, the energy required remain the same. For the second question, we transition into three-dimensional space to simulate a drone flight through a wind force potential field. The visualization illustrates a small 3D parabolic trajectory from the origin P000 to the landing pad Q221. We include a red arrow using the ax.quiver function to represent the force vector acting on the drone at a specific point in space. We utilize sp.diff function for each variable x, y, z to derive the gradient vector field. This tells us the exact force component in ijk influencing the drone's movement. To find the total work done, we again use the substitution function to calculate Fq minus Fp. And then the result for the computation yield is a 5 unit. This demonstrates that for conservative field in 3D, we can skip complex path integral and simplify the difference in potential between the start and end point. That's all from us. Thank you.